Hello everyone. So today we will talk about the soil chemistry. So the first topic we will discuss is about the introduction of the soil chemistry. And under it of the introduction of soil chemistry is the importance of soil in ecosystem function. Next is the role of soil chemistry in agriculture and environmental science, and lastly, the basic properties of soil particles. The first topic we will discuss is the importance of soil in ecosystem function. So the importance of soil is the medium land in which seeds sprout. They supply water, nutrients, and heat, all of which can be used to grow plants to maturity. Additionally, soil support a vast population of chemical elements, recycling bacteria, and fungi, in particular carbon and nitrogen, as well as hazardous elements. So a healthy soil is a dynamic living ecosystem, a complex combination of mineral and organic matter containing air, water, and life. Worms are critical to soil health, and without soil, planet Earth would be little more than a lifeless rock. Worms also burrows its way through the dark earth, ingesting particles of soil and expelling nutrient rich cast in a constant forage for food. Soil provides people with some essential building and manufacturing materials. Some countries build houses with clay, bricks, and drinks coffee from mugs made of baked soil clay. Water is served in a sand-glass silicon dioxide. So, by understanding the chemical processes that govern soil fertility and nutrient cycling, we can develop science-based strategies to enhance soil health, improve crop yields, and, and mitigate environmental impacts. So, what is agriculture? Agriculture refers to everything on a farm, including crop cultivation and animal and livestock care, typically done for a living. Farmers works hard to prepare soil, plant seed, provide water, and protect crops from pests and diseases. Agriculture requires much knowledge about seasons, weather patterns, and care for different plants and animals. So, what is fertilizers? Fertilizers can be either organic or inorganic substances that are applied to the soil or plant foliage in order to promote better growth. Next is the water-soluble fertilizer. Can also benefit from soil drench when applied to the plant. So, organic fertilizers improve soil structure and encourage the growth of beneficial soil microorganisms, which is good for plants and soil. Greener lawns last longer because organic fertilizers have a lower NPK analysis or the nitrogen, phosphorus, and potassium analysis, but provide longer term feeding. This has a sub, sub, subtle effect on plants and lawns. Artificial or the inorganic uh, fertilizers come in liquid, pellet, granule, and spike forms and are water soluble and fast acting. They nourish and green the soil quickly, but they don't promote long term fertility or soil life. They can burn lawns if applied excessively and seep into streams. Reapplying on a regular basis is necessary. And inorganic fertilizers are dangerous because there are more they have more chemicals when it is applied in the plant or in the soil. So here is a example of the illustration of the organic fertilizers and chemical fertilizers where the organic fertilizers is feeding the soil and the chemical fertilizers is feeding the plant. Now we will talk about the role of chemistry in environmental science. So the physical, biological, and mineralogical properties of soil are impacted by climate change, making environmental soil chemistry important. So, and acidification, pollution, desertification, salinization, erosion, and nutrient imbalances are all putting enormous stress and strain on our soils. So, what is carbon sequestration? So, sequestration is the capture and storage of atmospheric carbon dioxide. It is one for reducing the amount of carbon dioxide in the atmosphere to mitigate global climate change. So, what is soil texture? It refers to the proportion of sand, silt, and clay sized particles that make up the mineral fraction of the soil. Texture affects many soil processes, including the infiltration, drainage of the water and air distribution, erosion, chemical processes, and biologic processes. So here are the soil texture, and it is determined by the following method. First one is the mechanical sewer shaker, which is the soil is being shaken until it uh, goes down to the smallest particles of the soil, turning into a sand. Now, next is the sedimentation, which where we see the um, nahate uh, separating, where we see the separation of the clay, silt, and the sand. Next is the hydrometer. The hydrometer, where they test the density of the uh, soil, where where they uh, where they taken the soil particles or the soil uh, substances that they taken. And the next one is the pipette. The pipette, I'm not sure how they work, but they use it for the soil analysis also. So soil structure. Soil structure describes the arrangement and organization of soil particles in the soil, and the tendency of individual soil particles to bind together in aggregates. Aggregation affects water and air transport, which affects the movement of solutes and pollutants and affects biologic activity, including plant growth. Soil color. Soil color is largely determined by the organic matter content, drainage conditions, degree of oxidation, and in some cases, presence of specific minerals. Soil color is not a widely used factor in stormwater application. So, soil density. Soil density is related to the mineral and organic composition of soil and soil structure. The standard measure of soil density is bulk density with the gram or the centimeters cube. Bulk density affects water and air transport in soils. Soils with high density resist water and air transport. Soils with high density may also impede root growth. Now we will talk about the soil consistency. So soil consistency, it provides a means of describing the degree and kind of cohesion and adhesion between soil particles as related to to the resistance of the soil to deform or rupture. Soil is useful in estimating the ability of soil to support structures such as buildings and roads. Soil temperature. Soil temperature is affected by climate, water content of a soil, soil color, soil cover, or the presence or absence of mulch, depth in the soil profile, and air and water flow within a soil. Minnesota soils are generally slow to warm in spring due to climate, but the following conditions affect temperature.
My topic is about soil formation. Soil formation occurs continuously but slowly from the gradual breakdown of the rock by the process of wintering. Wintering can be physical, chemical, as well as biological process. The soil considered to be one of the most essential natural resource and is the best for the growth of vegetation on which our nutrition and livelihood depend. Soil is also the main source of which many microorganisms such as earthworm, crab, and several other species lives. The main soil form continuously but slowly form a gradual breaking down of the rock by wintering. There are five factors influencing soil formation. Number one, parents material. Few soil whether directly form underlying rocks. Those gradual soils have the same general chemistry as the original rock. The material in which soil form is called parent material. The parent material is mostly printed by chemical and physical processes and transposed, which is then deposited to form layering of soil. Bedrock is usually the parent material, but soil also gets transposed because of factors like wind and water. Number two, organism. Organism includes plants, animals, and microorganisms and food. They play a vital role in the formation of soil and are important determinant of the impact on the physical and chemical environment of the soil. Number three, climate. Soil formations refers heat and moisture. In case the climate is dry and cool, the rate of soil formation decreases. The prevailing climate conditions determine the nature of wintering process, the place and rates of both physical and chemical processes. Climates affect the kind of vegetation in the area, which affect the process of soil formation. Number four, topography. Topography refers to the configuration of the surface of the land and the relation of land with man-made and also natural features. The shape of the land and also the position of the slope and the landscape are important parts of topography. Number five, time. Time. The time it takes for soil formation affect the quality of the soil. Soil formation tends to take place over thousands of years by undergoing significant change and eventual formation soil with certain age certain age brackets and young and tend to have weak soil horizon development. That's all. My name is Wahid Muhajir.
Hello everyone! Today I'll be talking about soil components and minerals in soil chemistry. First is the soil particles like sand, silt, and clay and each part properties. And the second is mineral composition of soil. So let us start with the one of the three soil particles, which is sand. As you can see in the PPT, the definition of sand is a vital multipurpose natural material. Is used in various manufacturing and construction activities. It is made up of finely divided rocks and mineral particles, which have a range of properties of sand that make it important in diverse applications. This particle size, shape, and composition of sand can differ greatly, influencing this behavior and suitability for different uses. The unique properties of sand, like its ability to compact under pressure and provide stability, make it an important ingredient in concrete, mortar, and asphalt. Sand is a key component for construction, but it also affects soil health and coastal dynamics in environmental and geological context. This article discusses the technical properties of sand, like physical and chemical properties of sand, and highlights its role in the construction environment. So let us start with the one of the three soil particles, which is sand. As you can see in the PPT, the definition of sand is a vital multipurpose natural material. Is used in various manufacturing and construction activities. It is made up of finely divided rocks and mineral particles, which have a range of properties of sand that make it important in diverse applications. This particle size, shape, and composition of sand can differ greatly, influencing this behavior and suitability for different uses. The unique properties of sand, like its ability to compact under pressure and provide stability, make it an important ingredient in concrete, mortar, and asphalt. Sand is a key component for construction, but it also affects soil health and coastal dynamics in environmental and geological context. This article discusses the technical properties of sand, like physical and chemical properties of sand, and highlights its role in the construction environment. And the second is grain shape of sand. The shape of the grain is defined in terms of angularity as well as sphericity. The grains of sand range from well-rounded, sub-rounded, angular, and also very angular. Inside each angularity unit, grains can be of a high, medium, or low sphericity. The angularity of sand is measured by visual inspection using a low power of microscope. The best foundry sands include grains that have been rounded with medium to high sphericity, offering good flowability and high intensity permeability at low binder additions. More angular and lower spherical sand require a higher binder additions, lower packaging density, and poorer flowability. And the third is shape and distribution of the sand grains. The texture, size, and form of the sand grains are critical for controlling the consistency of the mold. Many of the mold aggregates are mixture of fresh sand and recycled sand, which comprise not only reclaimed sand but also more sand. In deciding the scale, shape, and distribution of sand grains, it is necessary to note that the grain shape corresponds to the amount of sand surface area and that the distribution of grain size influences the permeability of the mold. If the sand surface area increases, the volume of the bonding content, usually clay and water, must increase if if the sand is to be adequately bounded. As a result, a difference in surface area, possibly due to a change in sand form or the proportion of core sand being retrieved, would result in a relate change in the amount of bond required. And the last is the size distribution of sand. It influences the consistency of the casting. Coarse grain coarse grain sand allows the metal to enter the molds and cores, giving the casting a weak surface finish. Fine-grained soils produce a better surface finish but needed a higher bonding content and low permeability can cause a gas defects in castings. So we have here the chemical properties of sand. First chemical properties of sand is a soil reaction pH of sand. pH is a calculation of the concentration of active hydrogen ions or H+. It is an indicator of the acidity or alkalinity of the soil and is therefore defined as the soil reaction. The soil pH varies from 0 to 14 for values under 7.0 acid as well as values above 7.0 alkaline. The pH value of 7 is known to be neutral, where H plus and OH are equivalent all at a concentration of 10 to 7 moles or liter. The pH of 4.0 is 10 times more acidic than the pH of 5.0. The most significant influence of pH in the soil is on ion solubility, and this in turn determines microbial growth including plant growth. The initial pH of 6.0 to 6.8 is suitable for many of these plants and it fits the optimal solubility of the most essential plant nutrients. Few minor elements, example iron. And the second is the silicate clay presence in sand. The presence of silicate clay content influences the chemical properties of a soil mass. Clay particles have a wide surface area and are the best materials in a soil mass. Clay particles increases the reactivity of a soil mass and influences the cohesion of a soil mass by forming compounds with foreign materials. And the third one is the cation exchange capacity in sand. Any plant nutrients and metal occur in the soil atmosphere as positively charged ions or cations. Among the most important soil cations are hydrogen or H+, aluminum, calcium, magnesium, and potassium. Many heavy metals also occur in the soil ecosystem as cations. Clay and organic matter particles are primarily negatively charged or anions and have the capacity to keep cations from being leached or washed away. Absorbed cations are subject to substitution by other cations in a quick, reversible mechanism called cation exchange. The cation exchange capacity of the soil is indeed as estimate of the maximum of the negative value at a given weight of the sample, or the sum of cations that a given soil sample can carry in a interchangeable shape. The second soil particles, which is the silt soil. Silt, which is known to have much smaller particles compared to sandy soil and is made up of rock and other mineral particles, which are smaller than sand and larger than clay. It is the smooth and fine quality of the soil that holds water better than sand. Silt is easily transported by moving currents and it is mainly found near the river, lakes, and other water bodies. The silt soil is more fertile compared to the other three types of soil. Therefore, there is also used in agricultural practices to improve soil fertility. There are four physical properties of a silt soil, and the first is particle size. Silt particles fall between 0.002 and 0.05 mm in diameter. This makes them so small to be seen individually but can be felt as a smooth, powdery texture. In water retention, silt has a larger surface area than sand, allowing it to hold on to water more effectively. In drainage, the moderate size allows for good drainage while still retaining moisture. In compaction, salt particles are easily compacted, impacting the soil density and stability. The second physical properties is shape. Salt particles can be rounded or angular depending on their origin and weathering processes. In porosity, rounded particles create more air space within the soil, leading to a higher porosity. In permeability, angular shapes may create tighter packing, reducing permeability or the ability of water to flow through the soil. The third physical properties is a surface area. Silt has a larger surface area per unit mass compared to sand. In nutrient retention, larger surface area allows for greater absorption of nutrients, making them available to plants. In water retention, water molecules are attracted to the surface of soil particles, and a larger surface area leads to a greater water holding capacity. And now, let's proceed to the chemical properties of a silt. And the first one is the pH level. Silt soil typically exhibits a neutral to slightly alkaline pH level, ranging from 6.0 to 8.0. This pH range is typically suitable for most crops, providing a balanced environment for nutrient availability. However, variations in pH can occur depending on the specific mineral composition and the presence of organic matter. And the second one is the nutrient content. Silt soil is generally rich in nutrients, making it ideal for plant growth. It contains a balanced mix of essential nutrients, including nitrogen, phosphorus, and potassium, along with the micronutrients like calcium, magnesium, and sulfur. These nutrients are crucial for plant growth and development. However, silt soil can also be prone to nutrient leaching, where water washes away nutrients from the soil. Proper fertilization techniques and avoiding overwatering are essential to prevent this. And the third one is water retention. Silt soil exhibits moderate water retention capabilities, holding moisture for longer period than sandy soil but less than clay soils. This is attributed to its smaller particle size, which creates more surface area for water absorption. However, excessive water retention can lead to the waterlogging, which can harm plant roots. And now, let's proceed to the last soil particle, which is the clay. Clay soil is the most smallest particle among the other two types of soil. The particles in this soil are tightly packed together with each other with very little or no airspace. This soil has very good water storage qualities and make it hard for moisture and air to penetrate into it. It is very sticky to the touch when wet but smooth when dried. Clay is the densest and heaviest type of soil which does not drain well or provide space for plant root to flourish. In the other word, clay minerals are a group of minerals that are typically found in soils, sediments, and rocks. They are characterized by their small particle size, which is typically less than 2 micrometers, and their height surface area. Some of the most common clay minerals include kaolinite, smectite, illite, and chlorite. One of the unique properties of clay minerals is their ability to absorb and exchange ion, which makes them important for various industrial and environmental applications. For example, they are used as absorbents for removing contaminants from water and as a catalyst in chemical reactions. Clay minerals also play an important role in soil chemistry and fertility, as they can help to retain nutrients and water in the soil. They are also influence the physical properties of soil, such as their porosity and permeability. The overall, clay minerals are an important components of the Earth's crust and play a vital role in various neutral, natural, and industrial processes. Let's proceed to the physical properties of a clay. And the first one is the hydraulic conductivity. Hydraulic conductivity defines how easily pore fluid escapes from the compacted pore space. For a given deep water loading history, increasing sediment hydraulic conductivity increases the amount of pore fluid that will escape per unit time. On a macro scale, the gross sediment hydraulic conductivity is a function of both the amount of sand in the section and the literal extent of the sand. As you can see in the PPT, that picture illustrates generally hydraulic conductivity characteristics of the deeper continental margin used. And the second one is the swelling potential or volume change. It is defined as the ratio of increase in thickness to the initial thickness of the soil sample compacted at optimum moisture content in a consolidation ring and soaked under a token surcharge of 6.9 kPa. Seed et al. In 1962 so that the sample undergoes free swell. And now, what does swelling mean in soil? Swelling Shrink swell is the volume charge of that occur as the result of exchange in the moisture content of clay-rich soils. In other words, swelling soils, also known as the expansive soil, are the ones of the swell in volume when subjected to the moisture. Let's proceed to the chemical properties of a clay. And the first one is the silica. Silica, compound of two most abundant elements in the earth crust, which is the silicon and the oxygen. The mass of earth crust is 59% silica, the main constituent of more than 95% of known rocks. Silica has three main crystalline varieties. The quartz, that is by far of the most abundant, and the second is tridymite, and the third one is the cristobalite. Other varieties include cusite, keatite, and litchatelierite. Silica sand is used in the buildings and roads in the form of Portland cement, concrete, and mortar, as well as sandstone. Silica also is used in grinding and polishing glass and stone, in foundry molds, in the manufacture of glass, ceramics, silicon carbide, ferrosilicon, and silicones, as a refractory material, and as gemstone. Silica gel is often used as a desiccant to remove moisture. The second chemical properties of a soil is the alumina. Alumina synthetically produces aluminum oxide, a white or nearly colorless crystalline substance that is used as a starting material for the smelting of aluminum metal. It is also served as the raw material for a broad range of advanced ceramic products and as an active agent in chemical processing. Alumina is made from bauxite, a naturally occurring ore containing variable amounts of hydrous, water-containing. Aluminum oxide occur in the nature as the mineral corundum and its gemstone forms, sapphire and ruby. This can be produced synthetically from alumina and in fact are occasionally referred to as alumina. By the term is more properly limited to the material employed in aluminum metallurgy, industrial ceramics, and chemical processing. As you can see, this is the example of soil triangle texture. In mineral composition of soil, this is the solid or inorganic matrix, which consists of clay, silt, sand, and gravel. Depending on the proportion of each mineral fraction, a soil is classified into textural types. This changes both the physical and chemical properties in the soil and consequently affects its biological properties. The physical and chemical properties of the mineral components are closely linked to the soil texture and structure. Two key factors in decomposition: nutrient release, the fertility for plant growth. Texture refers to a percentage of clay, silt, and sand. Proportion of the soil. Various proportions have been given names, referred to as an soil texture types. Knowing the soil types is a useful indicator of how workable or malleable the soil is. Sandy soil are friable and clay soil are heavy and difficult to work, especially when wet. The structure of the soil refers to how these soil minerals component aggregate into large units, natural aggregates, called PIDs. Soil mineral particle composition and resulting soil texture. The soil texture triangle places soil into categories based on their percentage composition of clay, silt, and sand. To read the triangle, find the intersection of many components. An example is illustrated in that line. With a soil that was composed of 65% silt, 30% sand, and 5% clay. This triangle was proposed by the Soil Service Staff or USA and has since come into general use. See Service Staff in 1998. In that triangle, soil texture depicts a triangular diagram used in soil science to classify soil texture based on the percentage of sand, silt, and clay. The triangle's vertices represent 100% of each particle type, with the interior representing various combinations. The diagram is divided into regions, each representing a specific soil texture, such as a clay loam, sandy clay loam, silt loam, and more. The diagram helps visualize how different proportions of sand, silt, and clay influence the texture or properties of soil.
So today we will talk about the soil pH and buffering capacity. So the soil pH measures soil acidity or the alkalinity with a neutral pH of around 7. A change from 5 to 4 indicates a 10 times increase in pH in hydroplus, hydrology plus, and most soils have pH values between 4 to 10. Um, with low with lower or the lower have with and with lower having 5.5 to 7.5. Um, weathered soils have lower pH values. Soil with higher buffering capacity and higher CEC values CEC values requires additional lime or input to rise pH as um, the same management has a lesser impact on higher organic matter or clay types. So the importance of soil pH is it is it is sometimes considered the master variable that impacts plant nutrients and growth. Soil pH also impacts or interacts with other properties in the soil. The pH of the soil affects the availability of nutrients to plants, and certain nutrients are more abundant uh, in acidic environments, while others are more abundant in alkaline environments. Here it is example of the pH scale. So the 0 1 is the acidic, that is the battery. 1 for the stomach, that can lead to acidic stomach. 2 is the lemon, which is little bit more safer. And 3 is the vinegar. 4 the tomato. 5 is the coffee. And 6 is the for milk. And 7 is the water. And they say that from 6 to 7 are safe, or from the 8. And 8 is for the blood. 9 is for the baking soda. 10 is example stomach tablets, which where we and drink that are uh, tablets we drink for the medicine tablets, excuse me. And 11 for the ammonia solution. And 12 is for the soap. 13 is for the bleach. And 14 is for the drain cleaner, where we use for cleaning. So here are the factors influencing soil pH. First one is the parent material, nitrogen fertilization, management for a particular crop, the time, the buffering capacity. So now we are now in the soil organic matter. So the soil organic matter portion of soil that contains plant or animal tissue, known as the soil organic matter, has a number of benefits for soil productivity. Second is the majority of agriculture soils that yield are 3 to 6% organic matter. And last is this is a fact sheet describes its elements, functions, and field management techniques to maintain or um, gradually raise soil organic matter levels.
Our topic is all about the cycle in soil. The first topic is about the nutrient cycle in soil. Nutrient cycle is the continuous process through which nutrients move from the physical environment into living organisms and back again. This cycle involves the uptake of nutrients by plants, their transfer through food webs, and their eventual return to the environment through decomposition. This recycling ensures that essential nutrients remain available for use by various organisms, supporting ecosystem health and sustainability. The second topic is the nitrogen cycle in soil. The nitrogen cycle is a biogeochemical process that converts nitrogen into various forms, facilitating its movement from the atmosphere to the soil into living organisms and back to the atmosphere. Key processes include nitrogen fixation, conversion of atmospheric nitrogen into usable forms. The next is nitrification, conversion of ammonium to nitrates. Denitrification, conversion of nitrates back to atmospheric nitrogen. And decay and putrefaction, breakdown of organic matter. This cycle is crucial for maintaining soil fertility and supporting life. The third topic is phosphorus and potassium cycle in soil. Phosphorus in soil exists as both inorganic and organic compounds. Although total phosphorus levels are generally low in most soils, only a small portion is accessible for plant uptake. Many phosphorus compounds are characterized by low water solubility, limiting their availability to plants and affecting overall soil fertility. The fourth topic is potassium. The potassium cycle is a biogeochemical process that describes how potassium moves through different earth systems. The lithosphere, rock and soil. The biosphere, living organism. The atmosphere, air and hydrosphere, water. Potassium is essential for plant growth and is released from rocks through weathering, then absorbed by plants. When plants die or are consumed, potassium returns to the soil, where it can be taken up again or leached into water bodies. This cycle is crucial for maintaining soil fertility and supporting ecosystem. The fifth topic is sulfur and micronutrient cycle in soil. The sulfur cycle outlines how sulfur moves through the biosphere, earth crust, and biosphere living organism. Sulfur is released from rocks via weathering and then taken up by microbes and plants. As sulfur moves up the food chain, it is assimilated by animals. When organisms decompose, sulfur is returned to the environment, completing the cycle. This process is vital for nutrient availability and maintaining ecosystem health. The last topic is micronutrient. The micronutrient cycle in soil refers to the processes that facilitate the movement and transformation of essential trace elements necessary for plant growth. Okay, micronutrients include iron, manganese, zinc, copper, molybdenum, and boron. Soil microorganisms also help in the availability of these nutrients through decomposition and mineralization, ensuring that plants can access them in adequate amounts for healthy development.
Moving on to the next topic, which is soil contamination. Soil contamination occurs when harmful chemicals, pollutants, or hazardous substances are introduced into the soil, negatively impact its quality and health. As you can see in the first picture, manufacturer release their waste directly into the land toward the body of the ocean, followed by the farmers spraying pesticide or fertilizer, which one of the cause of soil contamination due to excessive use. Next one is improper local waste disposal on the land. Impact of soil contamination can greatly impact the environment, affecting ecosystem water quality and human health. It can harm biodiversity by killing soil organisms like earthworms and beneficial insects, which disrupts the food web. Toxic substances can also change the soil's structure, making it hard for plants and animals to survive. Soil contamination can harm human health several ways. People can come into contact with dirty soil while gardening, playing, or working outdoors, which can cause skin irritation and other health issues. Contaminated soil can also make crops and livestock unsafe. Plants may absorb harmful chemicals and heavy metals, making them unsafe to eat, and animals can eat contaminated plants or soil. Remediation to avoid soil contamination. First, biological treatment or bioremediation uses bacteria to break down substances in the soil. Second, chemical oxidation. Oxidation converts contaminated soils into non-hazardous soils. Third, soil stabilization involves the addition of immobilizing agents to reduce contaminants liability. Fourth, physical methods like soil washing use water separate and remove contaminants.